Welcome to GDP's Physics and Simulation 1. I am Felipe Bellini and this is a video demonstration of Project 1, addressing the classes lectured by Michael Feeney. All the information and source regarding this project can be found at both GitHub and Fanshawe Online. Project 1 features physics collisions and response simulation between game objects. For this proof of concept, I'll be using sphere-triangle and sphere-spheres collision algorithms. Now, let's go ahead and open Project 1's solution using Visual Studio 2019. If you have already seen the Graphics 1 project, you'll find this same structure. This solution features two main projects, Bell Engine and OpenGL Proj. Bell Engine contains the core functionality of our simulation. Its common code can be shared between multiple projects, simulating a natural game engine. Here, you'll find managers, such as the Physics Manager, which will handle our collision algorithms, the GPU Manager, and other classes to support game development. OpenGL Proj is based on Bell Engine and can be taught as the game itself. It contains code that's implementation specific for the project, such as animations, the level loader, which is a builder of levels, game objects, and etc., and the user control, which handles user input. The physics project makes use of the same level and game config descriptors found in the graphics project. They are located inside the assets config directory at the root of the OpenGL Proj. These files are loaded only once in the main. If you'd like to change the layout of a game level or the key bindings for user interaction, just alter these two files and restart the simulation. Here, as an example, is the game.cfg, displaying video properties and keyboard bindings. The level descriptor, or level.xml, features the camera configurations, the lights used in the level, and all the game objects that will appear once the program loads. Now, let's review the solution and demonstrate the physics project. I'm choosing to run this project from the bin directory for performance reasons. Once the simulation starts, we should see the layout described in level.xml being drawn on the screen. Although the simulation feels slow due to the continuous collision checking between game objects, we will be able to see the balls bouncing off each other and the other objects surrounding them. Our level has a number of physics experiments. On the left, we can see the interaction between a sphere and a ramp. The ball should be able to slide off it towards the hammer on the other end of the terrain. On the center of the screen, There's a moving platform based on a senoid algorithm. Balls should bounce at the top of the platform or be trapped between it and the flat terrain below. On the right, we have a rotating hammer. Balls can also interact with this obstacle by bouncing off it or missing it completely and falling off the terrain. On the back, we have a pinball or plinko experiment. As the balls fall down the machine, they should bounce off the cylinders and the user-controllable flippers. Press M or N to interact. Once one of the balls fall off the terrain, they will get destroyed when reaching a certain limit on the y-axis. This will cause a respawning at the original location described at the level file. Users can interact with all game objects shown on the screen. You can select one of the balls and apply a force to it, similarly to monkey ball, used as an example during class. Let's take the selected object and apply a force to it. By pressing Ctrl and one of the arrow keys, I'm applying a force on the Z axis. Notice that the purple ball is moving forward now. Now I'm applying a force to the right. On the Z axis again, you can see that the ball is slowly turning directions. In this simulation, we have two lights. Since it's not a requirement for the physics project, but it's good to have for demonstration purposes. There's one spotlight and the other one is a point light. Let's zoom in the pinball simulator to see the balls trapped in the boxes. Using the camera controls, let's move around. As we can see, some of the balls are trapped inside. We can also see some objects being respawned at the origin. We just saw a collision between two spheres here. Let's select one of the balls and cause a collision. Now I'm changing the position of the ball. That finalizes our demonstration of our physics project. For more information, contact Felipe Bellini and Professor Michael Finney at Fanshawe College. Thank you.